Thanks a lot, Mariana. So this is a new work with Renato, which is a PhD student at Pimentel University in Brazil. Probably he is online right now. His supervisor, Marcelo, Coniglio, and Elaine, which is here from University College London. And in a nutshell, so I'm going to present different semantics for modal logics, which is asking you to use.
Sorry. What is the microphone? Sorry.
You have to sign in.
Yeah, so I was saying, so because Renato is out there, so this I joined work with Renato Leme, which is a PhD student at Pimentel University. He's a supervisor, Marcelo Coniglio, and Elaine Pimentel from UCL College in which is here in this room. I don't know what to do.
It should be kind of
Yes, thanks. So, I'm going to talk about normal modal logics, which in this case, so we have this box operator. And since we have bottom and we have implication, we also have the dual, which is the diamond. With normal, so we are going to have modal logics in which we assume the necessitation rule, which is this rule that you can see here. So if you come through the theorem, then box of that formula is also appearing in this logic. And we also assume that the axiom K is there, which is the distributivity of the box with respect to the implication. Okay. So besides K and the necessitation rule, we are going to add some axioms, and this is well known that this is going to give you 15 different logics, normal modal logics, which is the modal cube. So this is the axiom that we usually assume DT equal 5, those are the axioms. So, and they are used very often in modal logics. So this is the kind of logic that we're going to treat here. And the usual semantics that we saw for these logics is the cryptic semantics, the relational model. So we have a set of words, as presented in the previous talk. We have a relation, accessibility relation on those words. And this is the semantics for box. So if every possible accessible word B in W, then we have to prove B. We have to prove the formula A in this word B. So this is the usual cryptic semantics. And then it's well known that these axioms, they characterize some frames in the cryptic structure. So for instance, the axiom D characterizes serial frames, the T reflexive frames, and so on and so forth. So the question that we address in this paper is, what about truth tables? So when we start doing logic, so the first thing that we do is truth tables, right? So what about using the same method for these modal logics? Well, bad news. So Gödel already showed that there is no finite value of truth function for impressionistic propositional logic. And then if we, so the encoding that we have of impressionistic propositional logic into S4 tells us also that for S4 we are doomed, so we cannot do it. And this was generalized by Eugene, showing that this negative result holds for the whole modal cube. So we cannot have just matrix semantics for all these modal logics. So we are kind of not dead end in this line of research. But then in the 80s, Kearns proposed a different semantics for modal logics. And as I'm going to show you later in a quote, he didn't believe in this notion of words for explaining modalities in modal logics. So the idea is the following. So he has a non-deterministic semantics matrix, sorry. So in the sense, for instance, so I'm going to tell you the meaning of these values. So if you have a formula with this value, then the box is not just a value for the value. So in this particular case, only 2. So we use this system for these 3 logics, S4 and S5, using only these 4 values. So this is the matrix. And then so what you can do is the following. So assume that we are going to prove P implies P. So if we look at the table, the matrix for the implication is going to give you the things in blue in the diagonal. So we only have T, big T, and little t. And then everything is fine because big T and little t, they are designated. So they designate something that is true, that is holds, right? So we are fine. Once we have, so everything is in S4 here. So this is also true in S4. And then we got these blue things here. So also we have 2 designated values, big T and little t. And then, bad surprise, if we try to apply the box to this tautology, which should be the case also in S4, we get this red ones, big F and little f. So it's not designated. So it means that if you apply this matrix, you don't get what you want, right? So you get something that should be true, but it's not a tautology in this matrix semantics. So somewhere fails. So it means that you build a table using these matrices, and then you have a tautology, but you have something that should be true, but you don't get a tautology there, right? So the solution of Kearns was to propose something called a level semantics, the evaluation semantics. And the basic idea is the following. So in a level 0, so in the first step, you use the matrix. And then for every single tautology that you see, you have to also have a designated value, so a T, big T, or little t value for this box A. So it means that if you look at this table, P implies P is a tautology, but we saw the red line, you don't get a tautology with the box, then you remove that line. And you continue doing this level after level. So in every single level, if you see a tautology, then you put also a tautology in the box, and then for doing that, you remove some lines. And this enforces necessitation. So every single time that you have a tautology, box A is also a tautology. Okay. The problem is that this is not a decision procedure in the sense that we have to check all the possible tautologies, and also if we see a false, a little f or a big F, we don't know if later this is going to be removed, right? So this is not a procedure. We don't know when to stop. So yeah, this is a semantics. I'm going to show you later that this is sound and complete, but this is not a procedure. Then later, Glatz, much later, proposed something called a partial evaluation. So when I say partial, is that we don't need to see all the formulas like in the level semantics, but we only see the formulas, the subformulas of the formula we are evaluating, like building a table. So Gratz, he proposes some complete decision procedure for these two logics. The idea is just build the table. You don't need to look at infinite objects. And the basic idea there is dependencies. So what Gratz does is the following, more or less in the level semantics. So you see this little t here is not well supported, which is a definition I'm going to give you later. So since this is not supported, it's going to remove this line, also and then we get again a tautology in box B implies. Okay? So this is the idea of support, and this gives you a decision procedure in the sense that you build the table until the formula that you are testing, and then if you get a tautology, so this is true. So it's complete. So the state of the art in this literature is the following. So Kearns level, so when we say level semantics, is the infinite object. Okay. So there are level semantics for 9 out of the 15 modal logics in the modal cube, and there is only decision procedures up to now for KT and S4. So what we do in this paper is to show that we can give level semantics, I mean infinite object, but also decision procedure for the 15 logics in the modal cube. And the good point of this is that we do it in a very systematic and modular way, meaning that I'm going to show you that we look at the meaning of the values of the logic, we classify those values, and out of that, we get the semantics. So there are different the semantics in the literature, but they always use different values and different procedures. So what we do here is just systematically producing them for all the 15 logics in the modal cube. Good. So just to finish this introduction, so Kearns in the paper says something like there is no words. So why we need to use words first for explain modal semantics, modal logics, right? And he says something very strong, but that doesn't constitute a useful fiction. So there are no words in there, right? So this is Kearns. I don't agree much, but anyway, so this is Kearns. And then later, Omori discovered, I'm going to show you that they propose some semantics for these logics. So they try to say, okay, the Kearns semantics is very easy, just build tables as we do for propositional logic. But what about the frame properties that we have in crypto semantics? And then they say, well, there is no simple way of looking or trying to put this thing together, the crypto semantics and the Kearns semantics. So in this paper, we reconcile somehow these two views. So I'm going to show you that the relational model on partial evaluation that we propose here satisfy the usual conditions for the frames that characterize the axioms in modal logic. So we kind of bridge the gap between these two semantics. So I finished the introduction here. So I'm going to start with the meaning of the truth values. And this is the most important part of the paper, is how we classify those values. And with this specification, out of that, we get the semantics. Okay. So the second part is the level semantics. Again, this is the infinite objects. So it's not a decision procedure. And later we refine that to a partial evaluation semantics, which is the decision procedure, how to build tables, and then with the concluding remarks. So let me start with the truth values. So Omori and Score, they propose 8 values semantics, level semantics for the logic K. So we have 4 F values and 4 T values. And what we do is to classify those values. So if you look at the red thing here, so all the F values, not A is the case there, right? So those are the F values, something is not the case. But dually, so we have 4 T values in which alpha is the case. We can do that also for the diamond. So those are the 4 values in which diamond R is the case. So we have 4 values like this. And also 4 values where diamond not alpha is the case. And we do the same for the box. So where alpha, where alpha is necessarily the case and where alpha is impossible. So box not alpha. So in a nutshell, so you have a value, and then this value, for instance, for this particular value, you have that beta is the case, but also diamond beta is the case, and diamond not beta is the case. Okay. So values gives you a way of saying if something is true now, there is a way of coming to a state where this is the case, or is always the case for every possible successor state. So we have that classification. So we have the D set in which alpha is the case. So we have the necessitation set in which alpha is necessarily, so box. We have the impossible set where box and alpha is the case. We have the P of possibility where alpha is possible, and we have the Pn where not alpha is possible, so diamond not alpha, right? So for instance here, so for this particular value, this is the formula, the characteristic formula of this value. Then it belongs to this set because we have the diamond of alpha. It belongs to this set because alpha is the case. And it belongs to the impossible set because this is the case here, right? Good. This is the classification. And then the question is, do we need all these values for all these logics? So there are 2 values, X2, T1, and F1, in which we have box alpha and box not alpha. So alpha is impossible, but it's also necessarily the case. And this can happen only if you have a state with all successor states, right? So in every single logic in which we have seriality, so we have a successor state, we don't need those values, so we can prove that they are irrelevant there, right? So, but this is a little example for one particular problem. So the idea is that we are going to look at the modal characterization of the truth values, and then systematically we are going to obtain the semantics for the truth value that we need for every single logic. So this is something like this. So for instance, if we assume the axiom D, so this is the axiom D, box A implies diamond A. So it means that V, so V's evaluation belongs to the set of N of necessarily. And then it means that it also has to belong to the set P, right? So, but there are some values. This one, for instance, belongs to N, but it doesn't belong to P. So we remove it. Dually, F1 is going to be more or less the same using the impossibility. So if you look at here, so it's impossible and has to belong to this set, but then F1 is not like this, right? So we did this with D and also with T, more or less the same recipe. So something which is in N has to be also in D, but this is not the case, for instance, for this guy. So this guy is in this set, but it's not in the designated set, so we remove it, right? So we look at the axiom, and then it gives you an idea the values that you need for this particular logic. So in every extension of D, we have 6 values. In every extension of T, we have only 4 values, right? And then we get the matrices. So I'm not going to bother you with that. So we have matrices for implication. It's the same for all of them. The only thing is that for some logic, for instance, this row doesn't exist because this value is not in the logic. So there are many tables, matrices. So we have a table for every single logic extending with some axiom. So this is for K extended with B, with 4, with 5, blah, blah. So this is the family of the T values of the T logics and extension of T. And this is the matrices for extension of T. So I'm not going to bother you with those tables, but we have a way of generating those tables, and those give you the initial matrix for the logic, right? So the level semantics is about infinite object. So forget about the definition, it's the same as kernels. So we start with the level 0, so apply the matrices, and then the problem is that the necessitation is not there. So every single time that you go, so it's a certified definition, you move up above in the next step, and then everything that is a tautology, most of that has to be also a tautology. If it is not the case, so you remove that line. So you remove this valuation, it's not a good valuation. And then the definition of the semantics of inference is this infinite intersection of all the levels in the semantics, and it's fairly easy to prove that this is sound for the logic. So if you can prove it in the logic, then it's a tautology in this semantics. For completeness, this is something I would say new in this paper, is that we look at the characterization. So this is our definition. So we use the hinting completion for proving the completeness of the logic. And this is a definition of the characteristic function for a saturated set delta. So we define that. So this formula takes the value epsilon I. If and only if you can prove the characteristic formula under this saturated set. And that's it. So we do it with, so this is the example with KT, I'm not going to show you, but then we prove some adequacy theorem saying that if there is a maximal consistent set, then this function is well defined. Okay, it's a level valuation. And then using this, we can prove the completeness theorem. So again, this is already known, this technique, how to do it. So what is, I think, a little bit new here is that we just look at the values, right? And the values is going to give you, in a systematic way, soundness and completeness theory for all the logics. But as I said before, this is not a procedure, so we don't know when to stop. For some logics, this already known where to stop, but in a general case, we don't know, right? So we have these infinite objects, and we start calculating the infinite intersection, but we don't know when to stop. So now partial evaluation, the basic idea is the following. So instead of looking at this infinite object, we look only at the formulas of the formula you're evaluating, like building a table, right? So again, consider one value. So I took F2. So this is the definition of F2. So it's box alpha, not alpha, and also diamond, right? So diamond is a requirement. So you have to show me the existence of another evaluation where alpha is the case, right? So the diamond in our semantics, they are going to give us some, the need for showing another thing, the extensor quantification, right? So diamond alpha needs to be the true is the case. So in that particular case, we have to show me another evaluation big prime such that big prime is designated, right? So it's the case. And then we fulfill the requirement of the diamond. Yeah, but we cannot choose any valuation because we have also the box. So the box, for instance, tells you if something is necessarily the case, and you connect B with B prime. So these two are partial evaluation with one relation I haven't shown it yet. So the next one has to be designated. Otherwise, you fail to fulfill the necessitation rule. If you go to extension of 4, it's a little bit stronger. So if something is necessarily the case, and then you connect B with B prime, so the next B prime has to be also necessary, because box implies box. Okay, so this is a particular example for the necessitation 4. But again, so what we did is to play with these sets, and then we systematically obtain a relational model for all the logics. So let me give you some examples of that. So our relational model is something like this. So it's a set of partial valuation. So this thing in blue is a set of partial valuation with a closed subset of formulas. And this is the relation we are going to build on valuation. So, but it's very simple. So this is based on the following fact. So if you have a value here, which is possible is the diamond stuff, you have to show me another one, right? So you have to show me another valuation. And the same for Pn. The Pn set is the set where this is diamond not alpha. So if you have a diamond not alpha, you have to show me a non-designated value in this another evaluation. So again, diamonds are telling you that you have to show me another evaluation, right? But then the processes are saying that it cannot be any value, it has to be some particular values, right? So just so we look at the necessitation rule again, so we see the sets. So one say that it is an N in the necessitation set, and then B is connected with B prime, so B prime has to be also designated in that case. So we look things like this. So this is the existential, you have to show me this, and then this is in the N set, so the necessary set, and then this one has to be also designated. So we write this like this. So from T, you have to go to something like T, little, and the little t's. Okay? And this gives you the necessitation rule. So if something is necessarily the case, you cannot have something here which is not designated, right? And this gives you necessitation. And for the set E, which is the impossible set, is more or less the same. So from F, you can go to something which is non-designated. So from F, you have this existential, but then from this F, you can go. You have to go to something which is not designated. Okay? Good. And we play with that with the other thing. So with the axiom 4, if something is designated, it has to go to sorry. If it's necessary, it has to go to something which is also necessary. So meaning this is K. But these two guys are not in the set N, in the set N, then we remove it back. So this is the condition that we have for K. And we play with that. And then, so this is the recipe. So the recipe is taking all the axioms. Those axioms, just look at the axiom and say, if this is necessarily the case, then you go to something which is also necessarily the case. Okay? So those are the axioms of the normal modal logic that we study in this paper, and this is the dishes, which I'm not going to bother you with that. But then systematically, we take all this thing, the recipe, and this gives you. So for every single logic, so we have the conditions. Right? Don't look at this, just to tell you this is a semantic way generated, right? And the important thing, and what's very nice, you have these frame conditions, which currently despite the fact that we need words and the relational words, and Omonian scores say, we don't know how to connect this. So we show that these relations satisfy the usual frame conditions in the modal logic that we are using. Good. So this gives you a procedures in the sense that you start with the propositional atoms. So you put all everything in value. So we prove something that is called analyticity, which is the way that you can extend with a new column, right? So I'm using this analyticity theorem. You can show that partial valuation can be extended to infinite object, the level valuation. So they coincide somehow. And using that, we can prove soundness. So this is the proof of soundness. And for completeness, so we already have completeness of level valuation. So we need a way of using this result, but we have here finite object and in level valuation, we have infinite ones. So what we did is to show also this vertical graph for the free logic that we studied. So you show that when you restrict a level valuation, this infinite object, to a subset, a closed subset of formulas, this is indeed a partial valuation. And then using that, and again, so this proof is entirely guided by the modal characterization. We look at the values, and then we get the characterization function, and then we got the coanalyticity theorem. And from coanalyticity, we prove that every level valuation, if you do the projection to a closed subset, is a partial evaluation. It's a good valuation. And then using that, we see the completeness of the evaluation of all these logics, of this procedure. Good. To conclude, so it's important we can do this table by hand. So, so Renato has a system written in Rock in which he is able to compute. So after that, he produced optimal panel, and he is able to remove the tables. We use those tables to refine. So in the beginning of the paper, trying to refine the things, trying to find counterexample and finding getting right. But apart from that, so we have full makeup, full there are some needs there, but there are because we were tired and we didn't have time. But we have already the proof of this thing for S5. That's what we're going to get. Also, the proof of analyticity was interesting because it's the way of extending things, right? And there are many cases. So I use mod in this particular case for generate all the possible configurations and getting and showing that we are right. So for all of them, the extension is a good extension. Okay. So as future work, so the first one is that Renato and Marcelo, they have a system for intensionistic logic of 3 values. And so maybe we can combine what we have here and then try to produce M-matrices semantics for intensionistic modal logics. We are now studying with people in Belgium the case of non-normal modalities. They also have layered semantics for non-normal logics. And the idea is to try to see if we can do it also in this very procedure or systematic way of producing semantics for all these logics. The tool of Renato produced counter models. So if something is not true, he used a relational model to show you the, not the minimal for the moment, but of the given logics. And finally, so UCL, they are very interesting in ecumenical systems. So we already have a system with 3 values for so for logics, for ecumenical logics, combining classical logic and deterministic logic. Okay, that's it. Thanks.